Okay, so this is going to be the beginning of sort of the unsupervised learning segment of the seminar and the course. And this is actually an interesting sort of divergence from what we've been talking about so far, because in unsupervised learning, we're largely dealing with data that does not have structure as provided to us previously. And I think to me, this definitely resonates a lot more with the kinds of problems that I'm interested in personally, and I think apply to games and simulations or even creative content, because creativity doesn't deal in sort of supervised type of knowledge in a way. When you want to create something new, largely you do want to use the existing data that you have access to. You want to understand the world, and then with that understanding you want to generate some new thing. And so, as a sort of higher level philosophical statement about unsupervised learning, right, it's a very, very powerful way to approach a lot of problems where you don't really know what your solution looks like. And then, once you understand sort of the problem space that you're in by way of these sort of unsupervised techniques, you can then apply those learnings, those insights, to choosing, say, a particular supervised learning technique. For example, and this is going to sound a little bit meta, but it's true. Imagine a model that knowing what people's faces look like. No, okay, people is a bad choice, but say we have a model that understands objects and can give us images of objects, and then now we generate millions of images of objects, and we know what those images are of, what objects they represent, and then we use that to then train a classifier model or something like that. I know it sounds really meta, like where is the, how do we know, and then this kind of stuff, and that's sort of like the study of unsupervised learning. And if in a way you have to think about the human mind as proof that this is possible, because we're not born knowing the things that we know, and we ultimately do learn those things. And while you could say, oh, that's supervised learning, you have somebody telling you, right, at the actual neurological level, that's not exactly true, right? The fact that we learn how to speak, the fact that we learn that certain things are dangerous and certain things are not dangerous, and many, many things that have not been spoken or told to us directly, right? You can argue that it's a byproduct of evolution. Our neural networks, like our physical neural networks, are actually, emergent properties of how we've adapted and turned into the living beings that we are. But yeah, it's still kind of a how does that work? And I think unsupervised learning, and as well as reinforcement learning, as we'll talk about later in the course, will try to. I mean, I don't want to say that they try to answer that question, because they definitely don't. But they do attempt to sort of live in that realm of dealing with problems that don't necessarily have an answer, and that's to me very exciting. So let's dive into it. And again, this will be kind of like a very high level intro to it. We may go deeper. We'll go deeper into particular architectures and ideas, but the goal here isn't necessarily to explain exactly how all this stuff works. So to start off with unsupervised learning, let's kick off with the discussion of maximum likelihood. And the idea with maximum likelihood, and we touched on this in a previous lecture, is that given a particular data set, we want to come up with a probability distribution that essentially maximizes the likelihood that our data came from that distribution. If you think about it in a different kind of way, the idea is to come up with some kind of mathematical model that, given this model, we can recreate both our data, but ultimately the model that our data came from originally. So one of the intuitions here is that we want to maximize the probability of seeing the data that we've seen. And we're just maximizing, say we have a particular neural network that is parameterized by the values of theta. What we want to do is, given all of the values of z that we see, we'd like to have a maximal, we want to maximize that, meaning like what we've been doing so far with backpropagation, gradient descent, and so on, which we can do, right? We calculate this value here for all the z's in our mini batch. We determine the direction in which we can change the theta to increase the value of this sum. We move in that direction with our gradient descent step, and then we reevaluate the sum again, and we keep doing it until we converge, or after a particular number of iterations. One thing that you'll often see is, instead of maximizing the likelihood directly, we'll look to minimize the negative log probability of our values. And the reason that we do this is because often in a lot of these models that we'll see, not necessarily in this lecture, but later lectures, evaluating as you know, to figure out we're trying to maximize this. This is essentially our objective function. The goal is then we'll have to differentiate this function. We'll calculate the derivative, and calculating the derivative in some of the sort of topologies that we'll see of the logarithm is a little bit easier. One of the main reasons that that is true is because of the ratio likelihood of the technique. So we can actually determine that the gradient of log p of theta, we can know that that is going to be 1 over p of theta times the gradient p of theta, which is a little bit, well, I'm not going to go into it too much, but like we'll talk about that in a later lecture. So one of the kind of classic use cases of unsupervised learning is clustering. And so you can see here in this image on the left, we start off with a bunch of unclustered data, and we want to be able to sort of split this data up into a number of clusters. Say we know the number of clusters, or we're going to try a bunch of different clusters and then calculate some objective functions on them and see which one seems to fit the data best. But the idea, generally speaking, is that we want to maximize the likelihood of a particular data point being related to a respective cluster. And the way that we would do this is, given a number of k clusters, as you can see down here in the bottom right, the distance, the Euclidean distance between the cluster centroid, or the mean value of the cluster, the distance between that and the value that we see, and we sum across it, we want to minimize that for each respective class. So if we have, said a little bit more eloquently, say we split up our data that we've seen into a set number of classes, k classes, and for each class we calculate this distance from the center of from the centroid, and we want to minimize that. So in a way, you can kind of see on the right here, for this green data, we're kind of choosing this point in the middle of the green and saying, okay, well, the green values have the minimum distance from this, and so on and so forth. We'll talk a little bit about the technique here that's pretty commonly used, called k-means, in just a moment. But the overall result, as you can see, is a splitting of the data that otherwise looks just like a bunch of data in the same place, splitting it into 3 different categories. And keep in mind, the k of 3 is chosen here, so we could split up into more. We would get a different clustering. But one notable thing is, you can see there's a lot of these red dots sort of close together, and this correctly clusters those together to suggest, oh, there's some kind of relationship here between these red dots. They're all very close together, they're all very in the same place, and that suggests that they're of the same classification. Again, to sort of tie this to the underlying goal of this course, to talk about how to utilize this in simulation and games, you can see how valuable this particular technique could be in the context of, say, a game where you're trying to separate different sort of classifications of things, be it in an economy-based thing, or when you have a lot of different objects in a world and you want to figure out how to deal with them, or even just in optimization of particular graphics algorithms. Say I only want to apply updates to certain things when they have particular behaviors, and I want to cluster them into objects of high priority and low priority. So you can kind of see the general use case of here. Again, this kind of comes down to that idea I said in the beginning of how do you solve problems that are sort of about unknown kind of quantities. How do you observe the data that you see and make some sense of it and add structure to it? And this is kind of one very eloquent way to do so. The underlying algorithm is called k-means, and the k-means algorithm looks a lot scarier than it really is. You essentially, given k clusters, you choose k-means, and again, like, your data may have some kind of dimensionality to it, so your mean should have that dimensionality as well. And so what you do is you choose k-mean values, and your your space. And then you assign each one of your values in your data to the nearest centroid based on that Euclidean distance. So for each value, you calculate the distance between that value and each one of your means, and for the one that has the smallest distance, you then classify it and say, hey, this belongs to this particular class, and so on and so forth. Then now you have a set, k sets of values, and you run over those values and you calculate a new mean based on all of those values. So if say I have 100 values, I split that now into 20, 40, and 40 items. For each class, for like the first 20 classes, I calculate the mean, and that's my new mean. For the first class, I calculate for those 40 values the new mean based on those values, and that's my new mean for that class, and so on and so forth. And now I just rinse and repeat. And you know that you're done when the algorithm no longer changes the classifications. So if you haven't seen an update to one of the data points to a different class, then you do not. You're done. Now you might want to do this like once or twice, but actually that's not true. It converges immediately, because if the update hasn't changed your mean, unless you're doing some kind of stochastic, so you don't necessarily have to do this for all of your values. So if you're doing stochastic, you might want to run it for a certain number, or start to detect or measure the convergence based on some kind of like epsilon stop value or something. But the idea is sound. You can kind of see here on the right, this example kind of shows you. It's nice because it's animated. Let's wait. Cool. So you can see the blue dot is here. It's moving. The X and the red plus sort of, as you can see, start to shift and get closer to these centroids that essentially maximize the distance between these. And if you're aware of like the Voronoi, I forgot the name of the thing, but the Voronoi algorithm that essentially separates things, it's very similar. So this Voronoi spacing is visible here. But yeah, k-means clustering, very easy, simple, naive implementation that's quite effective. Another way to think about this is, say that we have a bunch of data, and we then say I want to have this data can be represented by essentially a combination of Gaussians, or a combination of some kind of distribution. And so in this case, it's a kind of similar to our previous idea, except now in addition to a mean value, we also have a standard deviation. And you can do this for other distributions as well, by the way. It doesn't have to be a Gaussian, it could be a uniform, and so on, although I guess a uniform is kind of just like what we talked about with k-means, if you think about it that way. But the Gaussians are defined by a mean and a standard deviation, and then our distribution is approximated as the sum of these Gaussian distributions for given a particular value of x. So I forgot to add that in this equation, my apologies. And the idea here is that we want to maximize this model. And so for each value, we plug in our value into this Gaussian, into the Gaussians, into the sum, and we calculate the values, and now we have a value. And now the goal is to just maximize that. And the maximization step is essentially, and again, like I said in the beginning of the lecture, I'm not going to go into super deep technical depth on implementing this, but you can kind of see that taking the derivative of a Gaussian is a pretty well understood thing, and so all you'd have to do is given the calculation of the sum of all these things, then calculate the derivative of that, and then it'll tell you which direction to go in terms of each particular Gaussian that you're seeing. And now you can kind of shift the means and standard deviations of your particular of your Gaussian respective to your data, and over time you'll eventually get to a combination of Gaussians where each cluster is very close to, associated with a particular thing. And the way that you would then evaluate which class a particular data point is associated with is you calculate the value of the Gaussian for that point for each one of the Gaussians, and the one with the highest value is the class that your object is related to. And as you can kind of see here, there's this sort of issue, for example, with this item, this red item that is sort of in the green maximal area, that even though it's technically from the red, it's going to give you the maximum value in green, and so you can kind of see how the evaluation is going to give you the wrong classification. But as you can sort of see, it's very difficult to really differentiate between green and red in this area where they're very clearly equally overlapping. And so this is a little bit better, I think, than the k-means, in the sense that you can capture much more complicated relationships, but it's a little bit like, you, for example, with k-means, you can't necessarily have this sort of squishiness where this area here is a particular class, and then right next to it is another class that's much more spread out. The k-means won't handle that particularly well, because the spreading is going to be uniform, in the sense that it's going to sort of try to maximize the distance between these means, where that might necessarily be correct. So the Gaussian mixture will actually allow you to have sort of a lot of different things kind of squished together when another thing really far away. So also known, this is also known as sort of like mode seeking, where your data may have many different modes, and the mixture of Gaussians will try, given that you match the number of modes in your data to the number of clusters that you're trying to train for, will at least capture those modes particularly well. And again, this is a little bit out of scope for this lecture, and we may talk about it in the context of other models and other architectures as we go through the course, but very interesting stuff, and this sort of really is at the backbone of a lot of these maximum likelihood models and just unsupervised learning in general. This idea, you'll see it actually in many, many, many models, and still the concept of sort of matching the distribution of your real data, because you can imagine the underlying distribution of the data kind of looks like this bumpy thing, and what we're doing is we're determining what that data looks like by way of this sort of approach. So imagine we don't have classes or clusters, we're just looking at data, and this will properly represent the probability distribution of our data in general. And that's what we want to see. Say we want to generate a new data point that is real, and that's something that we would then now just sort of run the dice on our probability distribution. So neat stuff. Another use case for unsupervised learning is what's called dimensionality reduction. This is right here is actually an example of t-SNE, which we'll talk about in just a lecture, in just a slide or two. But the underlying idea of dimensional reduction might not make sense immediately. Like, why would you want to reduce dimensionality? Well, a good example is this image here, where now we have this image that represents all of our data in a way that is visually decipherable. So I can kind of see, oh, there's a cluster here, there's a cluster here, and this is actually supervised data, right? We already know the labels for this data, but we can kind of see that these like cone bipolar cells sort of stick together, and maybe if these axes meant something a little bit more than just sort of being a cool picture, we can start to say, oh, well, rod bipolar cells are more common in age groups. I don't know what the hell any of this stuff means, but the point of this is being able to sort of determine against axes, specific axes, what our data means. An additional reason for dimensionality reduction is when we want to reduce the size of our data. For example, compression is a pretty classic example of this, where we want to reduce the size of our data in a way that reproducing it's going to be as close as possible to our original data. And there you can kind of hear that our target and our goal, our target and our original need to kind of match up as much as possible. And so if we can have some really unique ways to do that with unsupervised learning, we can potentially find a mapping between our existing data and a smaller version of it that doesn't lose as much of the information as we can. So in short, there's a lot of different use cases for dimensional reduction, be it creating simpler models, so I want to rip out certain features that don't actually matter, to compression of my data, to just better visual or semantic understanding of my data in sort of a fashion that is aligned with the underlying structure of the data rather than previously labeled examples. So here, even though these are labeled examples, the structure that's popped out is unrelated to the labeling, but it's good to see that they seem to kind of come together in particular chunks that are decipherable, and that might be a good thing. Say our data was all over the place, that might not necessarily be good. Maybe we made an error, or maybe there's no way to create a model that can actually determine the difference. We have very good data labeling. Somebody did a lot of work, but unfortunately, there is no correlation between the class and the data values in this particular view, for example. So a lot of interesting applications for dimensional reduction. So let's take a look at one of the more common ones. So principal component analysis was a technique that was actually developed in like 1933. So it's largely a linear algebra technique, not explicitly machine learning at all. It's just the idea here is you take your data and you essentially determine the eigenvalues and eigenvectors of the inner moment or the gram matrix of your data. And what you do then is you order basically these eigenvectors in order from greatest eigenvalue to smallest eigenvalue. So what you've done is you've sort of figured out the sort of space of your stuff, and you figure out which particular dimension of your data is the least momentous, essentially, right? If you think about this as an inner moment of a matrix, you are now sort of determining which inner moment is the least momentous. So a lot of moments there. But in short, you can do this with a singular value decomposition as well. But the eigen kind of decomposition approach is a little bit more popular from what I've read. But to kind of break this down, say I took this matrix and I've split it down now into this matrix W, which is essentially the inner moment gram matrix ordered from least to greatest. We can now multiply this by our data, right, in this way, and this will result in a transformation, and that transformation is going to be a 1 by n by n by n operation, and the resulting is just going to be 1 by n. And so our transformation value is going to be equal to the same thing. But we can also shorten our W. So if we have, say, we want to remove the smallest eigenvalues, we can now have an L where such that L is smaller than n. And so if we multiply our x value by this W, right, we now have a transformation matrix that is 1 by L. And then the L in this case is going to be smaller than n. And with a little bit of chicanery here, you can kind of see that this new value t, it kind of represents a new transformation of x, so that is smaller than the original, and we can actually recover x by taking this inverse of nl times l and so on and so forth, and that result is going to be our new x, our new shortened x. So it's a very PCA gets pretty mathy, and if it's something that you're interested in, I'd recommend you check out the deeper kind of explanation mathematically of it. And almost every single machine learning framework has basically just the PCA algorithm for you. In fact, when I've implemented in the past, it's essentially just utilized the SVD implementation of like MATLAB or Octave. So it's not common to see people implementing this one from scratch because it's just largely a bunch of linear algebra. But if it's interesting to you, I recommend checking out the deeper math behind this. But the sort of intuition, again, is you are figuring out what part of your data is not interesting, and sort of projecting your data into a space that does not have that dimension. And so you can kind of see here in this image, the reason I chose this one is you can see this data that's sort of highly correlated in this sort of one dimension, right? And so in theory, I could project all of that data down to that green line with the minimum loss of information. And so that green line is a basis of my data, as you can see, and that basis then carries the maximum amount of information about my data, whereas this pink line has a lower moment, a lower covariance, and so as a result, if I was to, essentially for these two, it's a two-dimensional space. If I were to project this down into one dimension, I would choose to do so on this green line, and now I have this transformation that, when I undo the transformation, I'm going to get these data points, but they're all going to be on the green line. So they're going to maintain this spacing of this, but they're no longer going to maintain the spacing orthogonal to that line. So you can kind of imagine this as a very like brute force projection onto a particular set of bases in your data. So it's very effective, but it has limitations. As you can kind of see in the top right corner here, this is a principal component analysis done and run on MNIST. MNIST is a data set of characters, like handwritten black and white characters, and you can see that like they're not very correlated. What this is doing is it's taking MNIST, which is I think 32 by 32, so it's like 1024 features for each image of black and white, and it's projecting it down to two principal components, and then coloring it based on its label, because these images have values of 0 to 10 or 0 to 9. And you can see in some cases, like I think that's the 9. The 9 seems to have a lot of, if you think about letters or numbers, 8 and 9 are going to have a lot of pixels in a similar place, and so they seem to kind of like occupy similar areas in this PCA analysis. But for the most part, it's noisy, right? You have some over here, you have a bunch here, they're all over the place, and they're all on top of each other. The PCA results don't actually sort of segment and separate our data in a particularly good way if we want to visualize it on this sort of two-dimensional axis. So I'm not going to go too deep into t-SNE. So t-SNE is a machine learning technique. It's from 2008, so it's not that new, but it's a lot newer than PCA, which is from 1933. And what it's doing is it's actually a stochastic gradient descent approach. And what it's doing is it's determining both the distance from the pair, like the actual distance in space, but also as well as but both in the high dimension and also in the low dimension. So when we're talking about, I'm not an expert in t-SNE, so it's hard for me to explain it well. But the goal is to essentially preserve the distances in the classification space when they're close to each other, and so it takes into consideration both the distance in the overall dimensionality, so the L2 norm, just like PCA does, but it also adds to that the distance of the classes as well, and so this is actually done with a loss function. And so for the classification, for the entire data set, you calculate these losses. Once you do that, you determine the gradient of that and then apply it to the resulting distances associated with it, with the actual positions, these new dimensions that you're calculating. And so what you're doing is for each data point, you now have a X number of dimensions that you're trying to project into, and you're trying to optimize those for each data point bit by bit. So it's a gradient descent process. I know I slaughtered the explanation of that, but t-SNE results in a much better separation of classes as compared to PCA. As you can see here, the same MNIST data set has been run through t-SNE, and now when we look at the 9 class, you can see it kind of occupies this nice little island, and the green, like number 2, is over here. You still have overlay, you still have bleed, you still have situations where numbers, like for example, right here in the 9s, we see a fair number of 6s and what looks like 4s a little bit. But that makes sense if you think about it, right? Because a 9 and a 6, a 9 and a 4 actually kind of look pretty similar if you sort of map it out. And often when you look at MNIST on sort of like variational autoencoders and unsupervised techniques that are able to essentially interpolate the latent space or the sort of probability distribution linearly, you'll see these like 9s transforming into 4s or vice versa. So this kind of makes sense, and you can even see 9 as compared to 4 are touching each other, and similarly, well, I guess 6s are over here because I guess they're upside down. But 7s are right here as well, which makes sense because 9 and 7 are similar too. And there is this sort of relationship in a way that you can see, and also 1s are out here, which it makes sense. You know, if you think about it, the 1 is the only number that has this one long line and has a very distinguishable profile as compared to a lot of these other numbers, unless you do the little troop cheek thing and whatever. Anyways, this is pretty bad explanation of t-SNE, but you kind of get it. If you're looking to visualize and separate your data or project it into a space that is well defined and separate in classification. By the way, like again, keep in mind the classes come from the data set, not from the t-SNE operation. So if you didn't have the data set labels, you would just have this big blob, which is good, but now you've got to figure out like how these things are different. So that's a different subject. But yeah, t-SNE is a very powerful way to kind of make sense of your data, both in terms of maybe downstream utilization in other algorithms, or for just visualization purposes, as you can see here. So yeah, that's about it for this week, and next week we'll start to dig into generative modeling. Please let me know, like as I mentioned in the last lecture, if there's an interest in me digging deeper into LSTMs or in particular implementation of any of these algorithms I've discussed. Please let me know. I'll be happy to do so. And that's it for today. Thanks.